your measurements. To do that, you need a network analyzer, a spectrum analyzer, and amplifiers and power supplies, all kinds of stuff. So at some point here, probably by the end of tomorrow, we'll start rearranging tables. We'll get the two time domain reflectometers up. I will get the bullets, hopefully in an overnight package today. It'll have the bullets that allow us to take the last two network analyzers and put them in play. And we'll just have to spend, so we have so much equipment right now. We have enough tables, because clearly everyone has a seat at the table, but we are going to have to mix and match where the equipment is going to be used. So I'm going to talk a little bit here about the time domain reflectometer. And these are operating in real-time systems, and it's a sampling scope. Sampling scopes used to be absolutely critical many years ago before the advent of multi-gigahertz digitizers. Okay, when I was first starting out at Fermilab, we were able to obtain a 6-bit 60 megahertz digitizer from used aircraft. And it was one of these devices that was used in one of the military fighter aircrafts. And they sold us two of them for $4,000 a piece. It was a hybrid circuit, and of course, with 6 bits, that means you have 2 to 6 different comparators in it. And so this thing was just a cat's meow at the time. And we asked if we could get additional ones, and they said absolutely not, because we lost money selling two to you. And I think that maybe just said that the military said don't sell them anymore. I don't know. Because we were very careful with those two, and we put them into operation. And that was a fast digitizer, 6 bits, 60 megahertz, back, say, around 1980 or so. Well, as we all know right now, you can see it labeled on many of these things here, 10, 20 gigahertz sampling rates. So we're actually able to take many, many samples of an input signal of very high frequency, okay, with the modern scopes. But prior to that, we had to find another way to look at a very high frequency signal in the time domain by doing sampling. And if the waveform that you're looking at is repetitive, as many of the things we are doing here, if it's CW or even a repetitive pulse waveform, is what you can actually do is have a very fast switch and then some kind of an integrating circuit. In this case, it's just a simple RC circuit. And what they used to use and still do use, I change my batteries, is you can have a very fast Schottky diode tree that would allow the input circuit to pass through these things, which are acting as switches, to a storage capacitor. And you would do this in some differential mode. Now, depending on how fast I can turn a switch on and off, it would let a certain amount of charge go to that amplifier. And if it was a very to that capacitor. And if the capacitor was of very high quality, it wouldn't have very much leakage before the very next sample was taken. And therefore, I could then, as was on the first slide there, is I can reconstruct a waveform by randomly sampling a very high frequency. I'll get another sinusoid, but I will, because I know what my sampling rate is, the undersampling would still allow me to understand something of a very high frequency signal. Okay. Well, the technology for using sampling gates is not used at all in scopes anymore because of the high speed, high number of bit digitizers. But what a time domain reflectometer is, it's like a closed circuit radar system. It allows me to put out a pulse out onto a transmission line system, and it's typically a very short pulse, but the important thing is an incredibly fast rise time. And we've already heard about Fourier transforms and all of that, is if you had a delta function in the time domain of a repetitive waveform, it looks like a delta function in the frequency domain as well. So a very fast rise time pulse has an extended bandwidth. And that's very good because now I can send out a sharp pulse. It will go out someplace. It's going to hit an impedance discontinuity of some kind, and it's going to bounce back toward me. And this is what a radar does, whether it's an airplane or not. It sends out a pulse and it waits for the echo to come back. In the case of a TDR, it's all in a nice closed environment of a very known characteristic impedance. And under those conditions, I will see a standing wave ratio of this pulse coming back and forth, which will either add or subtract from itself on its return. Of course, if it's a perfectly matched system, nothing comes back, in which case you don't see any distortion on the reflected waveform whatsoever. And that's an interesting thing. And you can make one yourself very easily, And when I used to bring the resistive T with me, all you need is a step generator and a resistive T, because the resistive T has incredibly wide bandwidth, so the pulse goes through on both ports, and one goes to your oscilloscope, and one goes out into the real world here, and then bounces off and comes back. And so that's the poor man's time domain reflectometer. Now the important thing about a TDR is you want to be able to have very good time resolution so that you can see where the discontinuity is located. If you have a very slow rise time, slow even being 1 nanosecond, which is kind of like 500 megahertz of bandwidth, then you're not going to be able to see resolution to much better than, say, a foot. Okay, we talked about nanosecond of propagation per foot. So if you're trying to look for something, in the case they do this, there's an electric company at Fermilab that we hire routinely called thumpers. And what thumpers are is they come up with this green truck, and they have a high voltage pulsar in the truck, and they pulse your electricity line, basically your feed thing, sending 13,800 volts wherever your site is, and it sends out a pulse. And of course, at the discontinuity now, this pulse is not the little dribbly fraction of a volt thing that comes out of our TDR, but they're sending some serious joules out. And when it hits the nasty spot, which is typically a short or open circuit, there's a voltage breakdown at that point. And the voltage breakdown, whether it's just like lightning, is you get thunder that follows the lightning. And the reason why they call them the thumpers is they can now echolocate where the thump happened, and that's how they know how to dig to find out where the bad part of the cable is. Okay, well, we're not going to be doing, sending out all kinds of thousands of joules to make noise, but the concept is exactly the same. And in our case, we want to have incredibly high rise times. And so these boxes here, we'll look at it when we finally put the plugins in, but these rise times are typically on the order of 20 to 30 picoseconds. Very fast, sharp pulsars. They're typically done with a tunnel diode that's biased. And anyone who's ever worked with tunnel diodes knows that static will kill them. I'm impressed that we're in humid Arizona, because as I drag my feet across this carpet, I don't get sparks, which is really good. Carpet in an RF microwave lab is a no-no. And when I first went to work at Fermilab, they had carpeting on the floor, but the engineers who were there when they were putting the building together says, okay, if you're going to insist on carpeting on the floor, there was very nice conductive screen put under the entire carpet, and it was grounded. So you never got a shock in that RF lab. And then it turned out that they finally did get rid of the carpet while I was still there, and there's all this beautiful screen that was in the garbage can, and that became the new screen for my porch. You can hear that from me. So now if we take a look at what could happen in echolocation land here, and you're going to see this really clear on these guys. And the beautiful thing about, there's a computer in these guys as well, is as you can imagine now, this pulsar is going out, and it's seeing various impedances, which could be real or they can be imaginary. But there's going to be voltage steps, as you can see what's going on over here. And because it is a real voltage divider, if you just made the cheapo one that I showed you earlier of an oscilloscope with a pulse generator and a resistive bridge, the DC offset goes up and down depending on what the load discontinuity is. These boxes are pretty clever to where they end up taking that out for you, so that you always see the step function, and then some physical time later, it'll either step up or down depending on whether it's an open, short, or some variable reactive impedance. And the amount of voltage these things will spit out is very small. You can't get much more than a few tenths of a volt out of a step recovery diode. And you certainly don't ever want to hook anything into them other than this just reflection that it's capable of doing. So now, of all the equipment that we have in this room, it's probably the least used in the real world, but when you need it, it's something that becomes invaluable. The mystery boxes here, okay, the mystery boxes that are alphabetized, those are the ones we need for the TDR, and they got scribbled A, B, C, D on them. The other ones are the mystery loads for when you're going to do your matching networks, although you could do a mystery matching network to these as well. It's not impossible to do. Okay, and you're going to measure them. I'm not exactly sure if A, B, C, and D here correspond to A, B, and C there, but this shows you what happens if you have a series R and L, which means some kind of inductance discontinuity. Let me change these batteries because I think the laser is shot. Polarity's got to be correct. Remember that, guys, when you hook up the amplifiers. Let's see if I'm right here. Yay. Okay, so if I have this pulse now, and I have an R and L here, we're going to look at this in an intuitive fashion, is because we now understand what R's, L's, and C's are. Okay, a capacitor looks like a short circuit at high frequencies. An inductor looks like a short circuit at low frequencies. All right, and vice versa at high frequencies for each other. So if I stick a pulse out and it comes across an RL, in this case in series, well, initially that high frequency of that step looks like a high impedance. So the first thing that happens is the reflected waveform looks like an open circuit. So the reflection coefficient is +1. So the blip that comes back is positive at first. But as time goes on, because remember the Fourier transform is going to show that, eventually the pulse gets some DC response. So you'll end up seeing that it has to come down. But it doesn't come down to a short circuit, which would of course be -1. It comes down to something that's concerned with the L/R series impedance. So you can tell exactly what's in that box by just looking at this signature. Likewise, if you have a parallel RC, the first thing it sees looks like a short circuit because the capacitor will end up charging up at some point, and then of course not be a part of a short circuit anymore, and the thing will end up coming up to a value that looks like a positive reflection coefficient. Likewise, inductor in parallel looks like an open circuit at first, but now it looks like a short circuit at long distance, so it looks like this, and series RC does similar. I hope and I believe in the printout you can actually read this a little bit better. This just squishes it to be in Adobe mode. Now, this is so how many times do you look for this? Well, a lot of times when you're thumping around, you're looking typically for a short or an open circuit. And I think, let me see if I have, there might be some things coming up here. If not, I'll go back to explain it of where else it would be useful. So the thing is, sometimes you don't know what L/R is, but what you can always measure is the decay time constant. And we can use the general rule that from the incident point to where you reach the asymptotic limit is typically 5 time constants. So you can measure that because, of course, this is a time domain instrument, and you'll be able to tell me what the L's, R's, and C's are in these mystery loads. And the other thing that's important is the timing from where something nasty happens is, remember, it's reflection mode, so it's just like S11, is the signal's got to go out, find the nasty point, and come back. So this additional step area here is 2 times the distance the thing is actually away from you. Okay, now if you don't have enough bandwidth, because your pulsar either has a slow rise time or your receiving oscilloscope doesn't have enough rise time, instead of seeing a nice sharp spiky thing here, maybe this thing just doesn't like me on, you see something that looks kind of pulse spread. Clearly a high bandwidth environment here shows the inductor's kind of right there, but where does it really start over here? You don't have the time resolution, so you can't necessarily, if it was so bad, and this is a serious issue, if you're digging up a transmission line, you dug in the wrong place, and that's kind of expensive, okay? But they're pretty good about when they're thumping and getting it to a backhoe is kind of a big old hole anyway. They don't miss it by more than a foot or 2. But for our purposes, sometimes the circuit can be kind of small, and you'd like to know, is the discontinuity on this side of the connector? Is it on that side of the connector? Is it a little bit ways in before it gets to the circuit board or the kicker or anything else? You can actually do a radar measurement of knowing where the discontinuity that's making your device not work is located. And that's a nice feature. And of course, with something like this, the resolution is literally on the order of picoseconds. remember I told you you can use a network analyzer, a wide band network analyzer also as a TDR, but to get the same resolution that these boxes will give you, you need like a 20 plus gigahertz network analyzer. So, you know, this is a very specialized tool, but when you need it, it's absolutely essential. Do I have any other things there? Okay, so a place where we ended up using this many times is as we built the stochastic cooling pickups and kickers, we would have, you know, and of course these things had to move around because in some cases, you know, they were running at either liquid nitrogen or liquid helium temperature, so you had to have some flexibility. So these things were built to be able to move around. This is the launcher into it, for instance. It's a strip line device. And it had to work when it was really cold and you didn't want it to break. And sometimes something would be bad. And what we did before we did anything is we would take the TDR and characterize every single spigot so that we had a map of what all the connections looked like. And once we had that, that was our reference. When it was cooled down, you'd check it again to make sure it was perfectly happy. And anytime you went through a thermal cycle, you'd be able to go back to see if your connection, because this thing is buried in a vacuum vessel under much, you know, super insulation and everything else. It became almost invisible. When we're actually doing the lab for this, you know, you'll be measuring a number of different things. We have different transmission lines here. These are 75 ohm cables. This little skinny guy is a mystery cable, which I can't remember its impedance, but you'll be able to tell me that. Agilent or Keysight supplied this interesting board which has coupled structures on there and some filters. That's something we can play with. The main focus will be is I've got a whole series of connectors. We have LEMO connectors, we have TNC connectors, BNC, Type N, SMA. I even brought a couple of APC 7.5s that could be screwed back to back and adapters. Eventually you're going to be sitting there and you'll just have a whole chain of these adapters together. You'll be able to see every single one. And the lab exercises, you tell me which is the best connector to use for RF and microwave purposes. And that's one of the experiments. You'll also be telling me in the ABCD boxes what's in them without opening them up. Okay? And if someone doesn't believe it, we can't open them up. It's not a secret. But the thing is, you can actually tell me what's going on about them without opening up. Another type of connector I have here, which is a very old style connector, and there's just a pair of them, are GR connectors. These are sexless connectors that were developed by General Radio, and they were one of the best RF companies there was back since post-World War until probably the 60s or 70s. So we'll just go through all of those things, and again, when you're done with it, don't hoard, you know, bring the things back. And this is, again, a very new TDR from what we had 3 years ago when we talked to class. So we've already had some good things here to where some people learned how to find the button to make these guys speak radio. And then over there we learned that scope has its own signal generator in there. So start sharing all the mysterious things, because there's no need to suffer, learning the gory idiosyncrasies of these pieces of equipment, because A, you may not see them again and you'd forget anyway. The intention is that you get the concepts, not have to worry about model 85C or something or whatever it does. Okay, so that's just a primer on TDR, which is quick. And then we're going to do the quickie thing on mixers. And then I'll do the noise talk. And tomorrow we'll wrap up things. Okay, so we've talked a little bit about mixers so far, and they happen to be in pretty much every piece of equipment that we have here, except for the time-domain reflectometers. And again, going back to a simple diode detector, this is what is typically has been in your AM radio. Is all you need is a diode and an integration circuit, and the RF modulation can be going up and down, in this case amplitude modulation. And if you start integrating all these little saw teeth, of course that envelope contains music or telephony or whatever you can put into the modulation spectrum. Now, diode detectors, which are coming in the care package today, we will be able to tinker with those. This will be like an extra credity kind of thing that we can make some measurements if people find time on their hands. And I say that because over the years we've had people Nobody finishes on Monday of the second week, even the really smart advanced guys, okay? Because there's just too many experiments to run over 2 weeks here. But some people will start to finish up on Wednesday and have a whole day or day and a half left over. So I make sure I bring enough extra stuff that no one can play hooky from that point. Diode detector, we've seen this before, where there's a diode curve, and one of the gentlemen in class says, well, what does it do? And I said, you're going to measure it, and you're going to tell me. And again, this is a very simple one where you bias the detector, and here's a mixer inputs where you combine those two guys, and the diode does the multiplying. Okay, I showed you this on the first day, that if you sit there and multiply the things, you get an upper and a lower sideband. Both sidebands have the exact same information. Orlando here asked, well, what's the importance of single sideband? Ham radio operators would always have some kind of single sideband because ham operators are poor people with nothing better to do. And they go out to the ham fest and they see an amplifier that's worth maybe a couple of watts or whatever, and they can get it for $100 and say, oh boy. And then they hook that up the antenna, and if I send out double sideband with that, both those pieces of bandwidth are sending the exact information, if I can filter that out by some clever technique, of which is either filtering or using hybrids, then I can actually get more power spectral density in just one half of the sideband. And now instead of talking to just Moscow, maybe I get over to China or whatever else too. So it just allows you to get to a much further place. Okay, we're going to be working here with several different kinds of mixers of various different ranges. Most of them are from mini circuits that I brought. And so if you guys got your computers, you can get on the internet and figure out what frequency they operate at, what power levels they operate at, or and frequency levels. Typically the IF outputs are DC coupled, and that's how you make a phase detector, and that's part of one of the laboratories. This lecture here actually will show you most of the basics of what you need. You saw this your first day. Most of what you need to guide you through the mixer exercise. And the mixer exercise is going to take two signal generators, one of which could be a signal generator and the other one could be an output for a network analyzer. We'll just have to mix and match to see what it is that we own here. So as the classes start to progress and you're finished with your spectrum analyzer basics kind of thing, now you know where most of the buttons are on the units. You'll sit there and we'll start using multiple different pieces of equipment because you're getting at the point where you're starting to measure systems as opposed to just little boxes. We talked about this the other day a little bit, the single and double balanced mixer. Here's one of the things you're going to measure is conversion loss. It's because unfortunately, you know, the mixer, when it does this frequency translation and it is sending something up and it's sending something down, well, that says right off the bat that the signal power is going to be, you know, be diminished. And in actuality, it's the signal voltage is diminished by, you know, by half, which means the power is down by a factor of 4, 6 dB, typical. But the device itself also has insertion loss above this split, and that's a function of how high quality the mixers are made. So in order to measure the conversion loss, you're going to need two signal generators, which will come from the sources I just mentioned. And the reason why I show us here putting some pads on there is the mixer is a nonlinear device, which means it's not always 50 ohms at all drive levels. And what we'll learn as we put an attenuator, which this can even be just something as small as a 3 dB pad, any signal that now goes through the attenuator and comes back through it, it provides isolation, which is double the value of the pad. And providing you have enough signal power, this provides basically some isolation to where you're really just measuring the mixer as opposed to the mismatch of the mixer. And so I have us putting attenuators on there, although in real life you would not necessarily do this. Certainly you don't want to waste local oscillator power and your IF signal, which is what you really want to deal with. You don't want to diminish it anymore either. And these guys, nominal double balanced mixers are plus 7 dBm, which is plus 10 dBm is 10 milliwatts, so that's 5 milliwatt drive. You'll measure all of that. I think we will pull out if necessary so that you don't have to necessarily use the spectrum analyzer to measure all these things. We also have power meters. I think there's at least 6 power meters that have come, 3 from Rohde Schwartz and 3 from NI have come. And we'll pull those out of the boxes too. So by the end of tomorrow, everything will be out. Then I'm just hoping by Thursday night I'm not here till 3 in the morning to put it all back. So we're going to measure conversion loss in the mixer. We're going to be able to measure the linearity and 1 dB compression point of the mixer. And that's important for all the reasons I told you on how you don't want to overdrive your network or spectrum analyzer, because it's going to, the mixer itself internal could start to generate false information for you. So you'll need this talk just to guide you through the lab, which you should be able to download as well. And then you're going to generate even and odd intermodulation projects, which you'll be able to measure. This will all be on a spectrum analyzer as well. Here's the setup for doing third order intercept. Now you can see we're starting to use a lot of our equipment. We need two signal generators. We need a combiner. We need a combiner. We have combiners. We have mixers. We have low pass filters. Low pass filter in this case may not be one of these components. We may just allow the signal level coming from the local oscillator. We'll look at it on a spectrum analyzer and see that it looks nice, so maybe we don't need a low pass filter. So you're starting to hog up a bunch of equipment here at this point. Isolation measurement is pretty important. Remember, we said on the double balanced mixer there's all those transformers in it, whether they be lumped or transmission line devices. And this will allow us to measure how separated the ports are from each other. And this is very important when you're down converting, so that leakage from one port to the other doesn't hit a reflection at that port and come back through and start generating even more intermodulation products. We'll also measure a phase detector. And here you see I got this little symbol that looks like a trombone line. Well, trombone lines are very expensive and we have lots of them, but they're heavy to bring. So what you'll be doing at the frequencies involved is putting different lengths of cable or bullets and barrels to physically change the length between the RF and local oscillator path from the splitter to the mixer. And you'll be able to sit there and plot out the phase detector response, and you get a transfer function of the mixer that tells you how many degrees per volt and per power that ends up going into it. If you're making a phase lock loop, that's a very critical component to know, is because the phase detector is part of the gain of the feedback loop. And the more volts you get per radian change, the higher the gain is of the loop. And you may not have to make that up with a noisy amplifier, for instance, in order to get that response. And the last thing that we'll end up doing with it is making a current-controlled attenuator. When I didn't really learn much about mixers in school, but one of my first projects at Fermilab was to make something called a paraphase modulator. The way we run the cavities in the main ring at the time is, if you wanted to make the beam reduced, we have 2 sets of cavities. There's cavities A and B that are driven from the low-level RF. And if I drive them in phase, of course, all the voltages, the beam sees the right voltage and it adds up. But there's a lot of beam manipulations you have to make to where you have to maybe adiabatically increase the voltage in order to capture all the beam without upsetting it too much. And this you would have learned somewhere when you take the fundamental physics course. So the thing is, here you use the beam as the combiner, and then I can actually take the vectors and paraphase them to where when they go exactly out of phase, I'd have 0 volts as far as the beam's concerned, because one cavity would give it a thing, and the other cavity would give it a this, and the beam doesn't get any extra energy that way. And I can sit there and do all of this fun stuff. Well, the combination of using a 90-degree hybrid and a variable current attenuator, I can do a 90-degree rotation on both of those vectors to do this paraphasing. And what you can actually use to make the variable gain on the vector motion is a mixer, because you can use it as a current-controlled attenuator. So I'll have you guys measuring. Well, here you need an RF generator, goes into a local oscillator. The output goes to the R spigot with the spectrum analyzer being your detector. And then here we have a current source, which can be one of the power supplies we have here. And we'll terminate that spigot in a 50 ohm attenuator, or a T, with a 50 ohm terminator on it. And we'll be able to control the amount of current there's a current and voltage knob on this thing. We don't want to go too high. I mean, you'll want to remember these things will burn out at a certain point. They're fuses. But you'll actually be able to measure how much power goes through this mixer as a function of this current. And it's a very, very high dynamic range and inexpensive means of amplitude control if you're doing a feedback circuit in analog. Of course, these days, much of the stuff is done digitally, but it's surprising how much a current controlled attenuator is still very useful in microwave, especially as you get to very high frequencies. As high as all these wonderful things are, if you're working up 10, 20 gigahertz, they may be digitizing at 20 gigahertz, but they're not having 20 gigahertz of analog bandwidth yet. So, you know, real microwave engineers still use analog stuff. Okay, so that's mixers. And we'll do one more here on noise, which is beefy, but it really tends to baffle people. So I'm going to try to de-baffle it for you. Let's see. I want the electric car.
Ralph?
Yes.
Can we start experiments on that?
Which one?
The lecture you just...
The mixers?
Yeah.
I think so. I don't see why not. Well, the mixers are here. All the other parts are here, yes. Now, the one thing to do, like I said, you should finish that first spectrum analyzer thing there, and then we just cross you off on that. And now, after today's talk, the only thing you won't have, because I didn't talk about the vector signal analyzer, but you guys are already using vector signal analyzers over here because some of these devices are really vector signal analyzers that are looking like swept spectrum analyzers in disguise. And I was going to just make a quick mention about that tomorrow on how they're working different from a swept signal analyzer. And then tomorrow I said I've got this RF talk for, but I want to use the PowerPoint version of this next talk because it's animated. I don't do animation anymore. You know, when all that PowerPoint business first came out, whoa, look at that, I can make cartoons move and all that. It's like, that faded quick. You know, for all the effort you put into it.
That's so great. Nobody does that anymore. Your system is not